Hello, and welcome to the third lecture in the Jabrah Statistical Machine Learning series. Today we're going to start talking about probability theory. So if you were following the previous lectures, we had start talking about modeling, and we saw that when we're given some data set and we're trying to create a model of whatever the situation that the data set is drawn from, sometimes there's some kind of error involved, right? We can not really perfectly model whatever that situation might be. Rarely can we do that. So there's uncertainty involved here. And probability theory actually gives us a way to quantify this uncertainty, right? Because we want to have some kind of confidence in the models that we create, right? We want to say that based on this data set, whatever this model can express this situation with this much probability or whatever, right? So since most of the models that we gonna be dealing with actually have this element of uncertainty, um, having a firm understanding on how to quantify this is gonna be extremely important. So we're going to be building. We're actually trying to build an arsenal of tools that we can use to, later on express our models in the best way that we can. So, having said that, let's actually get started with a bit of probability theory. We're gonna start off simple, um, but as we go in the future lectures, things might get a bit more complicated, but it's okay. I will make sure that I go step by step in explaining exactly what it is we're dealing with, right? So I'm gonna start with something very simple. So imagine that we have two boxes, right? So we have box one. I'm just going to draw it here. So this is our first box, and we have box number two. So yes, I'm gonna start. Right now I'm just starting with a simple example actually, before actually going into the theory and everything, because I believe this might be better for you to actually understand like some of the things we're going to be explaining here. So one thing I should note before continuing this example is that most of these things, um, like that we're going to discuss in this lecture, may be things you're already familiar with, um, but there are certain ways of interpreting them in the context of statistical machine learning, and they're going to be quite important. That interpretation is going to be quite important, and it's going to be the basis of most of the algorithms we're going to be dealing with in the future, or most of the concepts, whatever, they're going to be dealing with in the future. Um, but the core behind it is going to be something that you actually really simply understand. So even if you're familiar with probability theory, it might actually be helpful for you, of course, to go through this lecture. Having said that, so let's say we have these two boxes, and in the first box, right, let's say we have two apples, so that's one apple, another apple here, and six oranges, so that's one, two, that's the third orange, fourth orange, fifth orange, and sixth orange. So we have two apples and six oranges, and in the so let's actually give this a name, right? Instead of box one, let's call this the so this is kind of, let's call this the red box, right? This is our red box, and this will be our blue box. So in the red box we have two apples and six oranges, and in the blue box, let's say we have um, three apples and one orange, right? So this example is actually drawn from um, the book that we're actually using for this module, uh, just in case you're interested. So this is what we have, right? So suppose that we randomly pick, okay, let's just deal with one box, right? Let's just deal with the blue box, for instance. Suppose that we actually randomly pick like a fruit from the blue box, and we want to know like how many times do we kind of expect to pick the orange, and how many times do we expect to pick the apple. That's basically the context of it. That's basically what probability actually is. So if we think about it, we go like, okay, 1/4 times I'm gonna be expecting to pick the orange, and 3/4 times I'm gonna be expecting to pick the apple, right? Like this should be kind of obvious to you from just looking at it. Um, but then what happens in reality might be something different. Maybe we try to do this experiment once or even 3 times, and 3 times we actually keep on getting an orange, right? So let's say that the first time we try to pick, we get an orange. The next time we get another orange, and the next time we get another orange, right? Then we get an apple. Um, if we didn't know what was in this box, right, we might just assume, just based on this data set, that the probability of getting an orange is 3/4 and the apple is 1/4, which is completely wrong. So what happened here? So what happened is that the number of times we kind of tried this experiment is too small, right? So we need to try this experiment many times before we can actually say, the probability of us actually picking an orange is actually 1/4 times and 3/4 times, because the more you try the experiment, the more you get you get closer to the true probabilities that are being expressed. And I'm actually going to prove this concept to you with a short program that we're gonna just look over. But what we need to kind of do, like, so in this thing that we expressed, we've got a couple of things that we're gonna be dealing with. So the first thing is we either pick box 1 or we pick box 2, right? Or the red box or the blue box, or we pick orange or apple, right? So this is kind of like the things that we're trying to do, right? This is the experiment that we're actually going through here. So we're gonna need something to actually express these events that we're doing. So we call them events, right? So we call them events. And what are the events here? So the first event is picking up, or let me not use this word. The first event is choose red box or blue box, right? And the second event is choosing like apple or orange, right? So this is what we're calling our events here. So since this is kind of something that has probability involved with it, right? We don't kind of with some probability we might choose red or blue, with some probability we might choose apple or orange. So we need some way of actually expressing these events, right? So these events can be expressed by what we call a random variable, right? So we call it a random. So these are terms that you'll encounter as you go into statistics and probability and stuff like that. And I'm just trying to explain to you what they actually mean. So when we're dealing with a random variable, we assign it, like, let's say the first random variable that we're dealing with is b, right? So b is the random variable for the event of choosing a box. And then the other random variable that we might actually be dealing with is, let's call it f, and f would be choosing a fruit. So if you're looking at this, you might realize that the random variables are actually based on the events that we're actually trying to make, right? So the first random variable is choosing a box, the second random variable is on choosing a fruit. So what are the possible values that the random variables might take, right? So we know, for instance, that for event 1, there is a probability that b is equals to r, which is the probability of choosing the red box. And there's another probability that b is equals to, what was the other one? The blue box. B is equals to b. So we know we're either going to take the red box or the blue box here. And the second random variable we're dealing with is of choosing a fruit. So we know the fruit is either going to be an apple or the fruit is going to be an orange. So this is kind of like how we actually express the events that we're gonna do, like that we're gonna make. So either we're choosing a red box or a blue box, or we're choosing an apple and orange, and there's a probability associated with all of these events, right? So we just express them. So this is just a way of expressing the things that we're trying to do here. So having said that, we can actually go even further with this by actually expressing this, of course, as probabilities. But before doing that, I just want to take a step back and explain to you, kind of like prove to you why we say that the more that we conduct an experiment, the more closer we get to the actual probability of that experiment. So, for instance, if we're looking at the red box, we say that the probability of choosing an apple, well, we've got 2 out of 8 apples, right? And the probability of choosing an orange is 6 out of 8, right? So this is something you can say, but sometimes you don't actually have this kind of distribution. So assume you don't actually know these probabilities, and someone just gives you a box, right? They just gives you like box 1, right? And then all you can do is sample from that box, right? That means you can continue choosing and choosing and choosing and choosing, and then based on those samples, you're gonna compute the probability yourself. So maybe, like we said before, so that's another important term that we need to actually look at, which is sampling, right? So sampling here just means we are just we we take we take a fruit from box 1. Just imagine like you're given this box and you don't know what's inside. You take a fruit, you look at it, you record it, you put it back, you take another fruit, and every time you're doing this at random. And then using those samples, you're gonna try to actually estimate like what's the probability of me choosing an apple and what's the probability of me choosing an orange. That's actually what we're doing here. So instead of actually going through an example here, I'm actually gonna go through some basic code where we can actually look at what we're dealing with. So here we have box 1 and we have box 2. So let's just focus on one box. Let's just focus on box 1, right? So in box 1, we've got 2 apples, there's 2 A's, and 6 oranges, which are those O's, right? A is for apple, O is for orange. And then someone asks you, okay, imagine you don't know what's in box 1, and then you're trying to choose at random, right, from this box. So what Python does, of course, it gives us, there is actually a way where we can randomly choose from a box. So we can use numpy, so numpy is here, random module, so random.choice. This allows us to kind of so let me create a variable here called choices, whatever our choices are. So if we do numpy done random.choice from box 1, right, and let us choose 5, right, and set replace to be equal to true. So it should be true by default, but I just want you to know what kind of options you can do. So this is actually called sampling with replacement, right? So you can actually do sampling without replacement, and we're gonna talk more about this in the future, of course. But just so you know that this functionality is actually available to you. So let us print our choices here. So here our choices we get orange, 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 apple, and orange. So we get an orange 4 times and apple 1 time. So based on just this event, if someone asks you what's the probability of choosing an apple, you just say it's 1/5, like 20%, and orange is like 80%. But the true probabilities is for apple is actually 25%, and orange is what do you call it, 75%, because if we look back here, we have 2 apples out of a possible 8, and we have 6 oranges out of a possible 8. So this is what we mean by the sample size actually influences your probability, how accurate your probabilities are. The more you sample, the closer you get to the true probabilities. And then let's actually prove it here. So let's have okay, let's have probability of, so probability of choosing, let's say apple from box 1, right? Let's create a list of all those probabilities, and we're gonna have an array with the sample size. So let's just call it sample size array here. So of course I probably should have mentioned this before, but most of the things we're doing here, we're gonna just be assuming that you actually have basic knowledge in programming. So it doesn't have to be in Python, it can be in any language, because most of these things will be intuitive if you have some idea of how to program. So you don't need to be advanced at it, but if you have just some basic programming knowledge, you should be able to just follow like most of the things we're going to be doing here. So here we have a list where we are maintaining the probabilities of choosing an apple, and here we have another list where we have a sample size. So what we're going to do is, okay, let me actually remove this. Let's start with a sample size. A sample size of 10, right? And then we're gonna say while sample size is less than, let's start with just 1000. We're gonna sample from 10 to 1000. So what are we gonna do, right? First, with a given sample size, so let's say in the beginning the sample size is 10, we're gonna do what? We're gonna say np.random choice, right? np.random.choice. So we're gonna randomly choose from box 1. How many things are we going to choose? We're gonna choose sample size number of things, right? And let's replace equals to true, just so that you. So we're gonna attribute this, right, as this is our samples, right? So based on our samples, what is it that we're trying to do? So actually, let me, I'm going to just add a break statement here so that it only runs once. I'm going to print out samples so that you see what we actually get here. I want to make sure that you are following with what we're doing. So these are our samples that we received, right, based on this. So what are we going to actually say after we do this? We want to know how many times apple was chosen in this sample and how many times orange was chosen in this sample. It just so happens that we can actually make this computation by saying, so this is computing the probability, so this is the sampling probability of choosing apple, right? how are we gonna do it? We're gonna say the sum, right, of, let's say, samples, um, samples where they're equal apple, right? So maybe instead of this, I should say a. Actually, let me just put it like this so that it's very clear to you. Over the length of the samples, right? So if I print the probability of choosing this apple from this list that you see above, it should be kind of like 0.2. It's just showing that probability, right? So from the samples that we have, so we want to so I'm going to remove this break statement now. So we need to append, so probability of choosing apple, box 1, we're going to append whatever the probability of choosing an apple is, and from the sample size array we're going to append the sample size, right? And that's pretty much it. We're going to have an array with the probabilities and another one with the sample size. That's basically what we're doing here. Now we need to plot it. So plt.plot. So the first thing we'll plot is we're going to plot sample size array versus the sample probability of actually choosing this box. And we're going to actually, let's say, let's give it a color of red, and the label is, let's just call it sample probability, sampling probability. Right, so let's also plot at the same time. We know what the true probability of an apple is, so I'm just gonna put 0.25 here. We know that that's the true probability. We just want to compare how the true probability and sampling probability, like how they compare with each other. So let's plot this times the length of the sampling size array. We're gonna plot this against the sample size array, and let's make this plot green, and let's call this label is, so we'll make this our true probability, right? So we have this, and let's set our title is should be probability of choosing. So if you haven't used matplotlib before, apple from box 1, so if you haven't used matplotlib before, maybe this is actually a chance for you to get it. So this is kind of like what we're just plotting x-axis, this is y-axis, and this is the color, this is just a label. So maybe this can be an introduction to you to do that. I think it should be pretty clear. So let's do x label. So we're gonna x label and call this sample size. Sorry. And plt dot y label. We're gonna, this is our probability. And plt dot legend location. Let's just set it to best. Right, and let's show our plot. Oh, sorry, I made a mistake here. We should increment sample size. Right, let's increment it by 10 so that this actually breaks. Otherwise, it's always going to be 10. Let's Okay, so as you can see, as we increase our sample size, this actually, this graph, um, it actually approaches the true probability. Maybe it's difficult for, you should still be able to see it from here, but let's actually go even crazier and use a sample size of 5,000 just to illustrate this point. As you can see, in the beginning, when the sampling size is, when the sampling size is small, the probabilities are varying a lot, right? But as we increase the sample size, we are approaching the true probability here, as you can see. So as you can imagine, the further we go, then this is just going to be, as we approach infinity, then the probability is going to be 0.25, but in the beginning. So this is the importance of having a large sampling size, right? So it actually also goes to when you're creating a model, like having more data is actually going to be able to enable you to create even much better models. So sometimes it's not about the algorithm you use, but sometimes it's about actually having adequate data for you to actually create that model. So this should show you the importance of data, and it's just from an aspect here of probability theory, but that's also something you need to think about. So let's go back to the theory part of things. So we are actually we're done talking, of course, about some of these things. We introduced an example here. So let's actually give these things some values, right? So let's just say probability of B being equal to R of choosing the box is 0.4, and the probability of choosing the blue box is 0.6. So we are just given these probabilities. We assume that we know these probabilities are. So if you're asking where did these numbers come from, they just came, like, you know, you just assume that you already know this, right? Because it's going to be important later on for the computations that we make. And the probability of choosing an apple and the probability of choosing an orange, right? Well, now this starts becoming tricky, because once you know what those probabilities are of choosing a red box and the blue box, what's the general probability of choosing an apple, right? So this becomes a bit trickier, and we're gonna start talking about certain rules that actually enable us to actually compute those probabilities. So that's the basic idea here. So let's go back to some of the things. So why is it that we're saying the probability of choosing red and probability of choosing blue? Why is it that we have 0.4 and 0.6? We just chose these values, but one aspect you need to know is these events, right? Either you're going to choose red or blue, right? So that means their probability are summing up to 1. We call such events, like, let's say, we cannot choose both red and blue, right, at the same time, and we call such events as mutually exclusive events, right? Mutually exclusive, what does this mean? It means they cannot happen at the same time. So if events are mutually exclusive, that means that the sum of their probabilities should be 1. So in this case, choosing a red box and blue box might be one example that we have. So we introduced this general notion of choosing from red box or blue box. So we have this random variable that we called box, and the box can take 2 values, and those values are either red or they are blue, right? So we're gonna come back to this example a bit later, but first of all, so what happened here? Let's fix that. Okay, there you go. But first of all, let's look at the more general case, right? So let's take a random variable, x, right? It can take values xi, right, where I is equals to 1 up to, say, m. So here we're just taking a random variable x. It can, so in the case of the box can take the value r or b, where r is blue and r is red and b is blue. So we're now defining a more general case where you have a random variable x, and x can take values x1, x2, x3, x4, whatever the values is, right? So a random variable may be able to take multiple values. And we have another random variable, y. It takes values yj, where j is equal to 1 up to some value l. This is how we describe our random variables. So one thing you might think of, if someone asks you, like, what's the probability of choosing box red and, choosing an apple, right? Box red and apple. This is, so if you know the probability of choosing the box red and you know the probability of choosing an apple, so when they ask you the probability of both of those events happening, so choosing red and choosing apple, those are not essentially mutually exclusive, right? They can, like, you can choose box and choose apple. These events can happen at the same time, right? We only say that the events that cannot happen at the same time is, for instance, choosing red and choosing blue at the same time. That's one thing you should take note of here. So someone asks you this. So we're talking about joint probability. Probability of choosing red and apple. That's kind of the thing that's what's called a joint probability. So if someone asks you, given two random variables, x and y, where x can be box for box and y can be for, like, fruit, right? Just think of it from that context. They ask you, what is the joint probability, right? Probability that x is equals to xi, the probability that x will take some value xi, and y will take some value yj. So they're asking for this joint probability. So you think to yourself, okay, how do you actually compute this? So let's actually have some kind of diagram here. Let me use this color. Let's have a diagram here that's gonna help us better express what we're trying to do. So one of them is so I'm gonna just cut it off randomly like that. Right. So we're gonna have here we'll have yj, and then here we're going to have xi, right? So this is the possible values that xi can take. So xi can take values between 1, where this is 1 and this is m, and yj, where this is 1 and this is l. So these are possible values that these things can take. So these are just the x's. Let's just consider them as the x's. So on this grid, you're going to sample, right? You're going to sample all these events, and then at some point someone asks you, what's the probability that of choosing, say, this is in particular this yj, this particular value of j, and this particular value of I, and stuff like that. So you can actually express and say, this probability, what is it essentially, right? So let's say this experiment is repeated n times, right? So we repeat an experiment n. So this is number of trials. Where number of trials is how many times are we actually, like, given this, how many times are we performing this experiment where we're sampling from x and y. That's essentially what number of trials is in this case. So let's say this is the number of times we choose xi and yj. Let's just call this nij, just to make it very basic. So the number of times where we choose xi and yj is nij. Okay, that's given. Now that we have this, we can ask ourselves the question now, like, so what is the probability of choosing xi and yj? Well, we can just express this as p, x is equals to xi, comma, y is equals to yj, to be equal to the number of times where we actually choose this, which we just called nij, divided by n, right? The number of samples that we have. So out of all the samples n that we have, we chose xi and yj nij times. So we're just expressing this from a very basic standpoint, right? So this is what it is. And someone then asks you, like, okay, the next question I have for you is, what is the probability that x is equal to xi, right? So what's the probability that this random variable takes this value, xi? So what you're going to do is you're going to look at, okay, I'm going to look at this value, I'm going to look at this value, I'm going to look at this value, right? And I'm going to divide by n, right? Because xi is just this column here. When you're looking at xi, you're only looking at the number of times you're choosing from this column that's here. If I can have a very light color that can express, this is where you're choosing xi from, essentially. So given that this is the case, let's actually give this a, let's say the number of times there is, let's call this, let's say another color I can use, maybe blue. Let's call this ci, right? So ci is just the total of this column. That's what ci is. We're just giving these values because they're gonna these assignments, because they're gonna become important for us later on. So ci, so this is equal to ci over n, right? That's the probability that x will take this value xi. Of course, right now you might be wondering, why are we actually doing this? We're actually deriving certain rules that are actually going to be actually going to help us, like, deal with some of our probability computations. So this is ci over n, right, where ci is just the total of this column. So how else can we actually express ci? So ci is actually equal to the summation over, so what we're doing is we're looking at nij, but we're summing over this column. So this column is represented by j. So if we sum over all values of j, right, nij, we'll actually get what ci is, right? So in case this isn't actually too clear to you right now, that's okay. Try to understand it, of course, but we're gonna go back to this example where we're actually using the same rules, and you're going to understand, like, what exactly it is we're doing. But just try to follow this. So ci here is summation over j of nij. So essentially that means the probability that x is equals to xi should be equal to, well, we said probability that of x equals to xi is ci over n, right? And then we say this is the summation of nij, right? That's what ci is, right? So if we actually replace this, let's first replace this ci, and we will have summation over j of nij over n, right? But we know nij over n is actually equal to this thing here, right? So this is summation, so we can actually write this as summation from j is equals to 1 up to L, which is over j essentially, of p x is equals to xi, comma y is equals to yj. Right, we just replace this ni over n with this probability here. So as you can see from this now, we actually derived our first rule. So this is rule number 1. And what is this rule called? It's called the summation rule of probability. This is the summation rule, right? This is kind of the first rule that we're deriving here. And it's also called the marginal probability. So that's the marginal probability. Why do we call it the marginal probability? Because if you look at it from the diagram above here, well, we're kind of like summing up over all possible values of y, right? So we're kind of marginalizing the variable y because we're summing over it. That's what we call the marginal probability here. And that's how the sum rule is derived, right, from these experiments. Now, let's consider another case, right? Someone tells you that, okay, you've already chosen xi. Xi is chosen. Given that you've chosen xi, what's the probability that y takes some value yj? That's it. So, for example, given that you've chosen box 1, what's the probability that of actually choosing apple? So it's already given. So one thing is, how do we actually express this question, right? So we actually express it by using what's the probability that y is equals to yj given x is equals to xi. This is called the conditional probability. So it is conditioned on the variable x being equal to xi. Given this condition, what's the probability that y is equals to yj, right? Well, if you just look at this diagram here, you can say, okay, given that x is equals to xi, the probability that y is equals to yj is whatever nij is, right? Y can take either this value nij or this value nij or this value nij divided by all the total in this column, which is ci. So you should know that this probability, since it's conditioned on let me rewrite this again. Since it's conditioned on xi, that means the total number of samples you're looking at are ci, where ci is just what we have here. That's essentially it. So that's what this marginal probability is. Now you are given this. Okay, now let's find another way of expressing this. This is actually equal to nij over ci, right? Actually, let's look actually at something else, like probability of x equals to xi, comma, y is equals to yj. This is equal to nij over n, right? We saw that here, x equals to xi, it's nij over n. And this is actually, we can rewrite this as nij over c times, right, over ci, sorry, times ci over n, because this 2 will cancel out and you'll have nij over n. So we can rewrite it as this, but that also means we can actually rewrite it as probability of, so that means probability that x is equals to xi, comma, y is equals to yj is equals to the probability that of y is equals to yj given x is equals to xi. This term here is the same as this term here, right? So let me just highlight that. So this term that we have here is the same as this one here, right? So this is multiplied by ci over n. Do you remember what ci over n is? I can show you. It's right here. It's probability that x is equals to xi. So we're just replacing these variables. And with that, we actually come to our second rule, right, which is known as the product rule of probability. So you might have heard these terms before, sum rule and product rule. Here I'm just showing how they actually derived. So this is the sum rule and this is the product rule. So we can write them more compactly by saying our sum rule is that probability of x is equals to summation over all possible values of y, or probability of x comma y, right? And then our product rule says probability of x comma y is equals to probability of y given x times the probability of x. That's essentially what we're dealing with here. So these are our rules. So just if it's this was just to help you understand where the rules came from, but if you just want to what do you call this, you can just use them as is, of course, like but in case you're not a firm believer, this is kind of should help you believe. And using these rules, we're gonna derive a very important theorem, right? So let's actually get to it right now. So if we think about it, we said probability x comma y. This is actually the same as the probability of y comma x. There's no difference here, right? These two, there's actually called a symmetry relationship between these two probabilities, right? So there is actually a symmetry relation. So having said that, what we're dealing with is a probability of x comma y is equals to probability of y given x times the probability of x, right? And we should also say probability of we can also write it in this way. It's equals to probability of x given y times the probability of y, right? But since these are the same, right, so these are essentially the same. So you can either say y given x times px or x given y times py. So we arrive at the point where we say probability of y given x times probability of x is equal to probability of x given y times the probability of y, which means the probability of y given x is equals to the probability of x given y times the probability of y over the probability of x. This is known as Bayes' theorem. So that's what we have right here. It is Bayes' theorem, and it is quite important because this theorem is going to actually form the basis of some of the things we're going to be dealing with in statistical machine learning, some of the terms that we're going to be encountering. Having said that, let's actually move on. Right. So we start. So again, you might already be familiar with this Bayes' theorem, but here's the thing: we can actually express this in another way, and this expression is going to be very important in some of the things that we're going to be dealing with in the future, right? So we can actually rewrite this as probability. Let me actually use a different let me use a different color just for the denominator of y given x is equals to, so we say this is x given y times the probability of y. This is divided by probability of x, but we can write probability of x in a different way. What is actually probability of x? We know that probability, let me do a slight side computation here. Should I use an orange color? Yeah. So let's do a slight computation here. We know probability of x is equals to the summation over y of probability of x comma y, right? How do we know that? That's the summation rule. So that means this probability of x is equals to summation over y of p, what is this here? If you remember, it's x given y times the probability of y. Why do we say this? Because this and this are the same. This is the product rule, right? It's not the product rule, sorry. if we take the what you call it, where is it? Here, yes, it's the product rule for y given x times px. So that's essentially what we're applying here, x given y times py. So we apply the sum rule, we apply the product rule. So that means we can actually rewrite this. Instead of px, we can write this as summation over all possible values of y of px given y, right, times py. So this is acting as what we call a normalization constant, because if you actually think about it, essentially what this is doing, it's kind of trying to normalize, right, the constant to ensure that the probability that is expressed here on the left hand side is actually summing up to 1. That's what it's doing. It's kind of performing that normalization. So this interpretation of this is going to become, right now, of course, it might not be clear to you as to why we're doing this, but it will become important later on, and I will show you why, of course, like in future videos. So let's go back to our example. Right. So let's go back to expressing our probabilities for our fruit example. So let's start from here. So we're going back to this example here, where we're dealing with the boxes and the reds and the apples and the oranges and stuff. So, having said that, we know that the probability, now we're solving an our example using these rules that we derived. Probability of choosing a red box, this is equals to 4 over 10, we know that. Probability of choosing a blue box is 6 over 10. We just assume that we know these values. Now, let's look at the other probabilities. What's the probability that the fruit is an apple given that the box is red? Right. So we're coming here, given that the fruit box is red, the fruit probability that the fruit is an apple is 2 over 8, which is 1 over 4. We can just look at it from here. Right. So this is equal to 1 over 4. Right. Which means correspondingly, since this what you call it, probability that the fruit is an orange given that the box is red, right, this should be 3 over 4. You don't even have to look, because these two events, either you choose, if the box is red, either you choose an orange or an apple. Those two events are mutually exclusive, and that means that they should sum up to 1. That's why you have this 3 over 4. Now, the probability that, I'm just going to fill in the rest of the values here, that the box is blue, this is 3 over 4, and the probability, again, you can just check here, choosing an apple given the box is blue, that's 3 over 4. And finally, the probability that f is equals to orange given that the box is blue, this is 1 over 4. So we have expressed all this probability. So the first question someone might ask you, so question number 1, let's actually solve the question number 1. What is the probability that f is equals to a? What's the probability of choosing an apple? Just generally choosing an apple. What's this probability? That's what the question is actually asking. Well, you know, right, when you see this, you should be clear which rule you should be using. So let's actually solve this, right? Let's solve this first question. So first we're going to look at probability that f is equals to a should be the summation, right, over all possible values, we'll just call it k, by the sum rule of p, f is equals to a, the fruit is equals to a, and the box is equals to k, right? So we're going to look at all possible combinations where the fruit is an apple, but the box can be red or blue. So what are this summation entailing? Like, what is it equals to? So this is probability that f is equals to a given the box is equals to r, plus the probability that f is equals to a, right? Sorry. So essentially times the probability that box equals to R. So I made a mistake here. The summation rule is not given, it is comma here. So you can rewrite this as this, essentially, right? Times probability. So plus the probability that f is equals to A given the box is equals to B times the probability that the box equals to B. That's essentially what it is. So we're just summing through all possible values here. So what should this give us? So probability that the fruit is apple, given that the box is red, this is 1 over 4, times the probability that the box is equals to red, which is 4 over 10, plus the probability that the fruit is apple, given that the box is blue, is 3 over 4, times the probability that the box is equals to blue, which is 6 over 10. So essentially this is what we have, and this will give us 11 over 20. So if someone then asks you the next question, number 2, so question 2, they might ask you is what's the probability that the fruit is equals to orange, right? You can go ahead and do this whole computation, of course, but since these events are mutually exclusive, either you pick an apple and orange, essentially. Well, if you're looking at it from that high level, this should be equal to 1 minus 11 over 20, which is 9 over 20, because this should actually sum up to 1 and such. So that's another way of looking at it. So having said that, we'll need one extra page here. So we've looked at how to use the sum rule to actually compute this probability. Of course, first of all, you have this, and then you convert it to this conditional probability based on the product rule. Then you just replace the numbers based on the numbers that you have here. So this should be pretty straightforward. So another question that you might be asked, let's go to the final question that you might be asked here. So what is the probability that you're told that a piece of fruit was selected, you want to know which box it came from, right? That's the question. So what's the probability that the box is equals to blue, given that the fruit is an orange, right? That's the question. So the way you solve this is like, if you look at this probability, we don't actually have this information, but we have the probability that the fruit is an orange given that the box is B. So what do we do here? Well, that should be simple. We know probability that B is B given F is equals to O. This should be equal to probability that fruit is equals to orange given that the box is B times the probability that the box is B, right, over divided by the probability that the fruit is an orange. That's essentially what we're computing here. So if you remember, this is Bayes' theorem, right? And if you just replace the values, I'm just going to do this quickly. You have 1 over 4 times 6 over 10, right? Times 20 over 9. Try to convince yourself why this is. Just replace the values that we have here, that we computed here, and try to make these computations yourself. So this should give us 1 over 3. And if someone asks you what's the probability that the box is red given F is equals to orange, it's just 1 minus 1 over 3, and such and such and such. So that should actually cover pretty much what we need to know about this. So I just went through a simple example of how we can compute this probability, some interpretation of this. Now let's actually go back and take a look at the Bayes theorem once more, because this is going to be a very important theorem that we're going to be using. So we say probability that y given x is equals to the probability of x given y times the probability of y over the probability of x, right? So this was base theorem. So we can actually have an important context here, right? So this is also based on this example that we're using. So for instance, if we actually had been asked which box had been chosen before being told the identity of the fruit that was chosen. So for instance, in this example, we asked we're just told a piece of fruit was selected, right? And it was an orange, right? We know the fruit was an orange. And then, given that the fruit is an orange, we want to know which box was it selected from, right? But imagine we had been asked which box had been selected before we actually knew that the fruit was an orange, right? So we are just trying to find the probability that the box is equal to B, right? This is essentially what this is. So what we can actually infer is that probability that the box is equals to blue in this case, that's the most complete information we actually have, right? Because here we're computing the probability that the box is blue given that the fruit is orange. But imagine we didn't know the fruit was an orange. So the only information we have about the probability of the box being blue is PB is equals to B. This is all the information we have. So this, which is of course the same as this term, is what we call the prior, right? So the prior, the probability of the variable we're trying to estimate, right, before we actually know what it's conditioned on in this case. That's what the prior is here, because this is the most complete information we have about this probability, because it's the probability available before we observe the identity of the fruit. That's why you call it a prior. But once we're told that the probability is an orange, well, we know that this is the probability after we actually observe that the fruit is an orange, and we call this the posterior, right? So this is the posterior probability. So this is just these are just terms we're using to interpret these probabilities that we're actually computing. So just be familiar with these terms, because we're going to be using them a lot, like what's a prior, what's a posterior, and stuff like that. So knowing what that is and what it actually means is going to become quite important. Having said that, we're going to stop our lecture here, and in the next lecture, at least within this module, we are going to start looking at probability density functions, and we're going to further develop our arsenal when dealing with this topic. Thank you.